Hey, so hi everyone again. So a couple of logistical things just to start off. So the first one is the project. So you should have got some messages from me on Piazza last night saying that now is a good time to start looking for partners. Start like coming up with ideas. The ideas will be first come, first served. So if someone submits a project proposal, I need to put on the project proposal submission thing online on Gradescope, but I'll do that today. If you submit your idea first, then you get priority for it. And if someone else tries to do the same thing later, then they'll have to switch. So yeah, the sort of main focus will switch the project once we've had the midterm a week Thursday. But it's time to start really, if you haven't found partners, if you haven't thought at all about ideas, then now's the time to get going on that. Another thing is midterm grades are now online, if you haven't checked. All the details are on Piazza. Another thing I wanted to sort of announce / advertise is that next semester there will be a course that is officially Chemistry 195, but that's just for practical reasons. That wasn't time to get it cross-listed. It will really be like this one. It's relevant to chemistry, computer science, and physics. It's going to be taught by Birgitta Whaley, who has taught this class many times before. And is a brilliant lecturer, brilliant professor, one of the sort of original generation of quantum information people. So that's going to be on, I think the official title is Special Topics in Quantum Computing. But basically it's going to be sort of a natural follow-on to this course, just going into some more advanced topics, more sort of cutting edge areas and so on. So if if you think you might want to go into like actual quantum computing, quantum information research, or just you're really interested in it, maybe you enjoyed this class, maybe you're like, well, this class was terrible, but next, if it's not Jeff lecturing, then maybe it'll be a lot better. Then definitely encourage you to do that. Should be really good. Okay, so now let's get on to the actual lecture. So last time.
Sorry, really quickly, do you happen to know what the topics are in the special topics class?
Yeah, I'll send a Piazza post out today with like the full advertisement. I could find them for you, but we've got a lot to cover today, so I won't do it right now.
Great, thank you.
Okay. So last time we talked about a couple of things. It was quite a long lecture. The first was how you define sort of the distance, the distinguishability of two density matrices. And we talked about how, unlike for pure states, there's not sort of a unique natural preferred notion like the inner product. But there's a couple of ones that are useful that we introduced, which were what's called the trace distance and the fidelity. Okay. And the second thing we talked about was quantum channels, which are really just like how density matrices evolve in time, right? It's like pure state evolution is just unitary, but when you have density matrices, that evolution can be noisy, information can be lost from the system and disappear out into the environment, and so the right notion is quantum channel. Okay, today we're going to be focused on really one big topic, which is entropy, okay, in all its forms. And we're going to start not with any quantum mechanics at all. We're just going to start with the notion of entropy just in classical probability theory. Okay. So I should say, if you've done a lot of physics courses, then you may have seen some definitions, depending on how advanced those physics courses were, you may have seen some definitions of entropy that were a bit different to the ones we're going to do here. They can be thought of as a special case, like the Boltzmann entropy, K log n, can be thought of as a special case for everything we're going to be talking about. So what is entropy? It's this sort of very mysterious word. I remember as a kid, you keep hearing and sort of pop sci things about like entropy always increasing and how entropy was disorder, and it seemed like that couldn't really be a well-defined thing. It was all very confusing. The right notion of entropy is it's always a measure of the amount of unknown information about some system. There's a lot of different types of information of entropy because there's various different reasons that information can be unknown and so on. But entropy is always about what you don't know. Okay. And so really the sort of right way to start thinking about entropy is to start with something, not the entropy, it's called the surprisal. Okay. And what the surprisal is meant to be is it's meant to be a measure of the amount of surprise you experience at seeing some particular sort of outcome of an experiment or whatever that we can call little x. Okay? Equivalently, it's also the amount of information content that you learn by learning x. These are sort of dual notions. Okay? And so, it's called I of x, I for information, I for surprise. I don't know, there's an I in surprise. It's not at the beginning, but it's in there somewhere. And pretty obviously, how surprised you are at an outcome should be a function of the probability you thought that outcome would have, right? And more than that, you should be sort of more surprised the smaller the probability of it happening was. So this should be monotonically, f should be a monotonically decreasing function. Okay, so the amount of surprise at something happening with probability 0.9 should be smaller than the amount of surprise of something that you experience at something that had probability like 0.01. Okay. So at the moment there's a, this is very arbitrary. There's a whole lot of monotonically decreasing functions out there. But we're going to require one more condition, which is that we're going to require that surprisal at two independent events happening should be just the sum, should just be your surprise at the two things happening that were independent of each other should be just the sum of your surprise at thing A happening and your surprise at thing B happening. Okay? So just the sum of the individual surprisals. Yeah, that's a very reasonable condition to put on like what it means to experience a certain amount of surprise. And formally, this just means that our function f that determines the surprisal from the probability needs to satisfy f of some probability of x times some probability of y is equal to the surprisal just at x plus the surprisal just at y. Right. So my total surprise, sorry, that should be a plus, not a product. Let me try that again. Should be the surprisal at x plus the surprisal at y. This implies that your surprise at any outcome x needs to be proportional to log of p, but we want it to be positive, so it should be proportional to log of 1 over p. Okay. So if something happens with probability a quarter, you should be twice as surprised as if something happens with probability a half. Finally, what the constant of proportionality is just depends on the units we use for surprisal. But conventionally, we choose units. And these units are the units of bits, the number of bits of surprisal, so that p of x being equal to a half implies that the surprisal at x is equal to 1. Okay, this is just how we normalize surprisal to measure it in bits. So then that means that we get our final formula for the amount of surprise you should experience at some event happening, just log base 2 of 1 over the probability of that event happening. Okay, so if something happens, toss a coin, it lands heads, you experience 1 bit's worth of surprise. If you toss 10 coins and they all land heads, then you experience 10 bits worth of surprise. Okay. Now we're ready to connect this to entropy. Entropy is very simple. In this context, it's called a Shannon entropy, but we'll see after it's first defined by Claude Shannon, basically the guy who invented information theory. But basically any entropy should really look something like this. And it's just defined to be the expected surprisal when you look at you discover the outcome of some probability distribution. Right, so for example, tossing a single coin, then if it's heads, you experience 1 bit of surprisal. If it's tails, you experience 1 bit of surprisal. So the whole thing, the entropy of that coin toss is 1 bit, because on average, you'll experience 1 bit of surprisal. So just as a formal formula, we say that the entropy, Shannon entropy, which is normally called H of x, is defined as the sum over all the possible values little x that this random variable big X can take of p of x times log base 2 of 1 over p of x. Okay. So it's on average how much new information are you learning from the outcome of some experiment? Right. This is equivalently a measure of how much unknown information there was before you saw the outcome, before you saw what the actual state was. Okay. So just as, let's take the case where there are, let's say we have a biased coin. Okay. Where has some probability p of being heads, some probability 1 minus p being tails, then the entropy H is equal to minus p log p, or p log 1 over p, minus 1 minus p log 1 minus p. Okay, we can plot this as a function of p. So we have H, we have p equals 0, p equals 1. When p is a half, this is just H is equal to 1. Okay, so we have 1 bits worth of entropy. Okay, when P is 0, well, then we have log P is infinite, but P is equal to 0, and P is equal to 0 more than log P is equal to infinity, because logs of a big number are a less big number. So conventionally, this is defined as equal to 0. If P is equal to 0, so that term equals 0. We have 1 minus P is 1, but log 1 minus P is 0. So if the coin is so biased that the probability of getting heads is 0, then it has no entropy, right? Because we'll always, there's no unknown information because we know we're always going to get tails. Similarly, P is equal to 1. We know we're always going to get heads. There's no entropy there. And in fact, the full curve looks something like this. Okay, so our amount of average expected surprise at the outcome is biggest when it's really a unbiased 50-50 coin, because that's that's the point where we know least about what the outcome is going to be. Okay, so it's pretty natural definition. What about if we have two random variables, x and y, that have some joint distribution, P of x, y. So these are not independent things. They may be correlated. Well, then we can define an entropy, hxy, for their sort of, their combined entropy, total entropy, which is just a sum over all possible values x, y, the probability of getting that x and y times log 1 over p x, y. Okay. We could also calculate what are called marginal entropies, hx and hy. Let's just do hx here. Just defined sum over x, probability of x, log 1 over p of x, where p of x is just defined as you forget about y, you don't care what y is, and you just want to know the probability of getting x. Okay. So again, that's just ordinary definition of the entropy that we just defined above. But the key point is going to play an important role throughout this lecture, is that in general, the entropy of x and y together is not going to be equal to the entropy of x plus the entropy of y. In fact, this is only true if x and y are independent. Okay, so hx plus hy, you can rewrite this whole sum as a sum over xy, px, py, log 1 over px, py. That's only equal to this definition of hxy if pxy is equal to p of x times p of y, right? i.e. the two things are independent. Okay. So instead, what you have, you guys can check this, is that h xy minus h of just x on its own, it's not just equal to h of y. Instead, it's equal to something that we call h of y conditioned on x. Okay, so this is called a conditional entropy. And it's just equal to sum over x and y, p of xy, log 1 over p of y conditioned on little x. Okay, so this is just P of y conditional on x is just defined as P of xy divided by the whole probability of getting x, P of x. Okay. But this conditional entropy is telling you the sort of expected additional surprisal from learning x. So from learning y once you already know x, right? There's a very closely related concept called the mutual information between y and x. It's called I x colon y. Okay, and this is defined as sort of h of x plus h of y minus the joint entropy h of xy. Equivalently, it's equal to the entropy of y minus the entropy of y conditioned on x, or equivalently, it's equal to the entropy of x minus the entropy of x conditioned on y. Okay, and just as an explicit formula, you can check pretty easily, just given by the expectation of log of pxy divided by px times py. Okay, so this thing we'll show in a minute is always greater than or equal to 0, where with equality, i.e. it's equal to 0 if and only if x and y are independent. So this measures the amount of sort of shared information between x and y, right? It's the amount of overlap between the information in x and the information in y. Okay, that was a lot of definitions in a short space of time. So let's see an example. Okay, so let's assume x and y are both bits, so they're either 0 or 1. Going to assume that sort of p of 0, 0, of both being 0 and p of both being 1 is equal to a half. And the probability of them being different is 0. Okay, so x and y are just the same number always. It is random what that number is. Okay, so the entropy of x, well, what's the sort of marginal probability distribution of x? It's 50% of being 0, 50% of 1. So its entropy of that distribution is just 1. H of y is also 1. But finally, h of xy is just, there's 50% probability of both being 0, 50% probability of both being 1. And so yet again, we find 1 bit's worth of entropy, right? Hence, the conditional probabilities, the sort of entropy of x conditioned on y, the entropy of y conditioned on x, the entropy of x conditioned on y, are both equal to 0, right? If you knew x, you wouldn't expect to be at all surprised by learning y because you know what it's going to be, you know they're equal. Same vice versa. And finally, the mutual information, the shared information between x and y is equal to 1. Okay. Yeah, I should say also, yeah, this conditional entropy is also manifestly greater than or equal to 0. So this is as small conditional entropy as possible. It's also as large mutual information impact as possible. The mutual information is defined as the entropy of y, say, minus the entropy of y given x. So it's upper bounded by the entropy of y. And for something where y is just a single bit, then the entropy of y is at most 1. Okay. So this is maximal. This is minimal. So these x and y are perfectly correlated. That minimizes the conditional entropy of one and the other, and it maximizes the mutual information. Okay. Any questions about that so far? About all those definitions? So learning x gives you 1 bit of information about y. Any questions about how all that works?
I have a question. All
Yep.
these quantities are less than 1, right?
Yeah, for a single bit, they're all less than or equal to 1, but it could be, for example, that x is just an integer, right? And then it could theoretically be arbitrarily big, depending on the number of possible values n can take. They're all bounded by the logarithm of the number of allowed values for x.
Okay, thank you.
Y. Cool.
What would be like 2 bits of information?
So if I have a random number between 0 and 3, right, with 25% probability of being each one, or I have two numbers, each of which are random and independent and between either 0 or 1, right? Anytime you've got 4 possibilities and they're all equally likely, and you learn which one it was, then you get 2 bits of information.
Okay.
Cool.
Can I ask a question?
Yep.
So I remember, I think it was like 2 or 3 lectures ago, we went over the block sphere and how you can have like the pure states, which are basically just points on the, like where r
Yep.
equals 1, or you have like interior states that
Yep.
like are less than r. Can you construct something similar with like this?
So these are just probability distributions. So if you only have 2 outcomes, which is the equivalent of a qubit, right? You have a probability distribution on a single bit. That's just labeled by p being between 0 and 1. So it's right, the probability p of 0 being between 0 and 1. So it's just like the space of probability distributions is just a line. If there's more possibilities, then it becomes a higher dimensional thing. And basically it's just subject to the constraints that all the probabilities have to be greater than or equal to 0 and they have to add up to 1. So that cuts out some chunk of like Rn, and yeah. Does that answer your question? You can certainly, yeah, all these concepts of entropies and stuff will go across to the quantum setting. And we're going to do that in sort of the second half of the lecture. But for the moment, we're just thinking about classical.
Oh, okay.
Yeah, maybe that was your question of like, how does this work with qubits? Yeah.
Yeah, exactly.
The answer is that we're going to come to that in a bit. Cool. Okay. So before we do so, though, there's one other important thing we want to introduce. It's just classical, and that's the notion of relative entropy. You will often, in the classical case, you'll often also see this going by the name of KL divergence. Sort of stats and machine learning and stuff like that, they often call it the KL divergence. Relative entropy is a much better name. Makes it much clearer what's going on, but never mind. So this is conventionally written D of some probability distribution, P, relative to some probability distribution, Q, and it is defined to be the sum over X of P of X log 1 over Q of X minus P of X log 1 over P of X. Or equivalently, just in a more compact notation, maybe less explanatory in terms of what the interpretation will be, just equal to P of X log P of X over Q of X. Okay, so what does this thing mean? This thing is the extra expected surprise from having an incorrect knowledge of the sort of true probability distribution. Okay, so P of X is the true probability distribution. Q of X is what I think, call it my guess at the probability distribution. Okay, so if I think that the probability distribution is Q, maybe like I don't know that it's a biased coin, right? Actually, it's a biased coin, but I just think it's completely unbiased. So I think, for example, I think that there's a 50% chance of heads, 50% chance of tails. Actually, it's like 90% chance of heads and 10% chance of tails. So my expected surprisal is, the probability of heads is 90%. But if I get heads, I will still experience one bit of surprise because I thought that only had a 50% chance of happening. And if it's tails, that was only a 10% chance of happening, but I experienced one bit of surprise. So my expected surprise is still one bit, even though it's a biased coin. Okay, and then this whole thing is like my expected surprisal. And then this is just subtracting off the entropy, right? I like the inevitable expected surprisal just from the probability distribution. Okay, because if I knew the right probability distribution, I would experience P log 1 over P worth of surprisal on average. But in fact, because I had this wrong guess at the probability distribution that was Q, I experienced P log 1 over Q worth of surprisal on average. Okay. Unsurprisingly, if I have an incorrect guess at the probability distribution, if I don't know the true probability distribution, then I end up inevitably experiencing more surprisal than if I'd had the true, my expectations were the sort of true probability distribution, right? And there's a quality again, if and only if P and Q are just the same probability distribution, right? If and only if I actually had the correct guess. So the extra surprisal from a wrong guess is always positive. Okay, so we can prove that pretty simply. D of P relative to Q is equal to P log P over Q, but that's also equal to minus sum over X, P of X log Q of X over P of X. there's an inequality that log A is always less than or equal to A minus 1 for any positive number A, with equality if and only if A equals 1. Okay, so then we have D of P relative to Q is greater than or equal to sum over X, P of X, Q of X over P of X minus 1. Okay, with equality if and only if Q of X over P of X equals 1 for all X. And this is just equal to sum over X, Q of X plus sum over X, P of X. Of course, both of these add up to 1 because they're probability distributions. So that is just equal to 0. Okay, so this extra expected surprisal from incorrect knowledge of the probability distribution is indeed always positive.
What circumstances is this quantity useful in? Because it seems like to actually calculate it, you need to know P of X. So
yeah, it's more useful. Yeah, obviously it's a measure of how different the probability distributions P of X and Q of X are. It's also going to have some other useful uses. We'll see one right now. Let's say we want to prove that the mutual information between X and Y is greater than or equal to 0. Okay, so the mutual information is defined as the sum over X and Y, P of XY log P of XY over P of X, PX, PY. Okay, this is just equal to the relative entropy between the fold probability distribution P of X, PXY, and the probability distribution where you just ignore the correlations between X and Y. Okay, so the mutual information is just the extra expected surprisal from forgetting about the fact that X and Y are correlated. Again, it's then trivial from our previous proof that this is greater than or equal to 0 with equality if and only if PXY equals PXPY. So mutual information is the extra expected surprisal from ignoring the correlations between X and Y. But yeah, in answer a bit more to your question, it's completely true that you can only define the relative entropy if you know P of X. The right way to think about it is you're imagining some hypothetical person who has the wrong guess of P of X and thinks it's Q of X, rather than like you just think it's Q of X and you don't know about P of X at all. Okay, it's like a mathematical tool for ignoring correlations.
In your proof of the EPAQ, like from the second to third line, is that just not an equal sign?
It is an equal sign. I just used greater than or equals because I was imagining that there's the D.
Oh, okay.
D relative to Q is greater than or equal. But the actual going from the second line to the third line is an equality. Yeah.
Right, thank you.
Okay, so we're about halfway through the lecture, which is great because we're now going to move on to quantum mechanics again. Okay, so everything so far has been classical, but from now on, it's all going to be quantum. So there's a very natural question, which is, can we have these things called density matrices, which sort of capture probability distributions of quantum states. Can you define an entropy of a density matrix? The answer is you obviously can. It's called the von Neumann entropy. and it's just the obvious thing. So it commonly has the symbol S rather than H for the classical one. But S of some density matrix rho is just defined to be equal to minus the trace of rho times log of rho. Okay, remember, log of rho or e to the rho or any function of a matrix just means well, there's a couple of ways to define it. You can define it as using a Taylor series, or you can define it as just leave the eigenvectors the same, and you take the eigenvalues and apply the function to the eigenvalues. Okay, so in this case, this is equal to minus the trace of sum over I of pi, that's from the rho, times a log pi times the eigenvector psi I, and of course this is just equal to the sum over I of pi log 1 over pi, assuming this is the eigenvalue decomposition here, not just some random ensemble. Okay, so you just look at the eigenvalue decomposition of rho, and then you treat that as a classical probability distribution, and then you just take its Shannon entropy. Okay, but this has this nice compact form, just minus the trace of rho log rho. Okay. So we can also define conditional entropies for quantum states. And the easiest way to do that is just to directly define S of some subsystem A conditioned on subsystem B as the entropy of the sort of full density matrix, the global density matrix, rho AB, minus the entropy of just the reduced state, rho B. Okay, again, sort of exactly same as our classical definition, but now because we have both rho AB and just rho B involved, it's not as simple as it just reduces to the classical probability distribution for some particular ensemble. Okay. In particular, if we let rho AB be a projector onto the Bell state, 2 qubits, right? So this is a pure state. Then we have S of rho AB. Well, this is a pure state, so that's just equal to 0. Okay, the probability distribution is like probability 1 of being in the Bell state, probability 0 of being anything orthogonal to it. But S of just rho B on its own, well, the reduced density matrix rho B is equal to half times the identity on B. And so that has entropy equal to 1. Okay, so what this means is the conditional entropy of this entangled state is equal to 0 minus 1. So it's equal to minus 1, which is, of course, less than 0. Okay, so this is completely impossible classically. Classically, the conditional entropy represents the sort of extra uncertainty, expected uncertainty about A, conditioned on learning B. And that is just obviously positive. It's the expectation of a number that's always positive. But in quantum mechanics, it can just be negative. The analogous quantity can be negative. And in fact, having a negative conditional entropy like this is one nice hallmark of an entangled state. It can never happen without having quantum entanglement involved. Okay, so this is really quite weird. Yeah, it sort of destroys the like nice simple interpretation we'd like to have of the conditional entropy. But it, yeah, so you just sort of have to develop a new intuition for what the conditional entropy means. And there's no nice, simple classical interpretation in terms of like an expected missing information. But it turns out it's a very useful sensitive quantity. Makes sense to talk about it all the time. It shows up in lots of places. It just can be negative. Okay. Any questions on sort of the von Neumann entropy, the conditional entropy, or anything from the end of the classical stuff that you didn't get to ask about? Okay.
I think I had one question actually.
Yeah.
So I guess it's very minor, but I'm just kind of curious. Like I think at one point we defined this in terms of log base 2. Are
Yep.
these all still log base 2, but we're just kind of suppressing that, or?
Yeah, I got lazy.
Okay.
It for this course we'll make it always be log base 2. Generally speaking, anyone doing sort of information theory or computer sciencey stuff or anything like that works base 2. Anyone more physicsy will work base E. It just depends whether you want to be able to talk about like number of qubits or number of bits or something like that, right? That's much nicer to talk about than like number of nats, as they're sometimes called, which means like something with like E probabilities, which obviously doesn't really make sense. If you're working in physics, then it's just natural to work base E because everything's nicer base E. Yeah.
Oh, thanks.
It doesn't really matter. It's just units. But yeah, we'll stick base 2. But I got too lazy to keep writing the logs for base 2.
A question follow up on that. Can information be fractional, irrational, or imaginary?
So entropies can definitely be fractional. Yeah. So if some event happens that has probability, 1 over square root 2, then you learn log. Well, that's half a bit. Whatever. Just some arbitrary probability p, then you learn log p bits of information by seeing it, so that can be irrational. What you can't have is that like you can't have all outcomes convey an equal amount of information, i.e. be equiprobable, and still have them irrational, because you need to have a finite number of outcomes. Well, the amount of information, it depends what base you're working. Like the log can still be irrational. So I don't think it can be imaginary. I don't think that makes sense. Yeah, it's always classically, it's always
another
positive.
question too.
Yep.
So when we're talking about these summations of probability, so we considered like a case of X and Y, right?
Yep.
I can imagine you might have a system with say like hundreds of bits and some
Yep.
kind of interesting correlated thing. You would then have to sum in general over all 100 bits in order to get this correct.
Yeah, exactly. Yep. Okay. The things I schematically called like X and Y just represented like all the possible outcomes, right? So if actually your system consists of 100 qubits, then X is everything from 0,0,0,0,0 to 1,1,1,1,1, all 2 to the 100 possibilities. So it gets very, very big. That's why one of the reasons entropies involve a log is because otherwise it gets completely out of control. Realistic entropies are order 10 to the 20 something. Black hole entropies get up to 10 to the 70 something. If you were working with the actual number of states involved, then it's like 2 to that power. That's insane
I
numbers.
think I have a question.
Oh, yeah.
Can I relate this entropy with temperature?
Yeah, so we're not really going to talk about how temperature gets involved. Temperature gets involved because it's related to the gradient of entropy with respect to energy. That's how temperatures show up. That's really the definition of temperature, or inverse temperature. In this case, we don't have any energy, so temperature doesn't play a role. But yeah, that's why in information theory you don't have temperature. Does that answer your question?
Yeah, sure. Thank you.
Cool. Okay. So in general, anytime psi AB, some bipartite state, is just some pure state. Then we have sort of S of the reduced state, rho A is equal to S of the reduced state, rho B is also equal to minus the conditional entropy of B conditional on A and minus the conditional entropy of A conditional on B. Okay, this is just because psi AB, we have this Schmidt decomposition. You can always write it as, in terms of some orthogonal set of states on A and on B. And then this implies that rho A is sum of I lambda I psi I, rho B sum over I lambda I phi I. Okay, and these two have the same entropy. Okay, so this entropy captures the amount of entanglement, captures the amount of sort of unknown information about the state of the subsystem that still exists even when the global state is completely known. Okay, so it's the amount of unknown information that exists because the state is entangled. For that reason, it is often known as the entanglement entropy. Right? It's the entropy created by the entanglement between A and B. Okay. That's sort of just an aside. Another thing that we had classically, we again have quantum mechanically, so we can define a mutual information just in the obvious way. It's defined as the entropy of rho A plus the entropy of rho B minus the entropy of rho AB. Okay. So for two sort of classical bits or C bits, two classical numbers that were either 0 or 1, we had this bound that 0 was less than or equal to the mutual information between A and B, less than or equal to 1. And this bound came from the fact that AB is equal to SA minus SA conditional on B, which was less than or equal to SA on its own because the conditional entropy was positive, and in turn S of A was less than or equal to 1, right? Because any probability distribution on a single bit was less than or equal to 1. For 2 qubits, we still have that the mutual information is always greater than or equal to 0. And this is generally true in quantum mechanics. We'll prove it in a minute again. And this equality happens if and only if rho A is equal to rho A tensor rho B. But there's now no obvious reason it has to be bounded above by 1, because there's no reason that this conditional entropy has to be positive. And in fact, the mutual information can be as big as 2. So this happens, for example, when rho AB is equal to the Bell state, phi plus, right? So then the entropy of A is 1, the entropy of B is 1, but the entropy of the AB is equal to 0 because it's just a pure state. Okay, so in this sense, mutual information is a measure of sort of correlations. And what's happening is that entanglement is allowing sort of super correlations, like correlations bigger than you could have classically. This is spiritually very similar to the fact that entanglement lets you violate Bell's inequalities, right, for correlations between different things. Okay.
Do negative entropies imply that some probabilities can be bigger than 1?
Yeah, so entropies aren't negative. Okay, in quantum mechanics, the von Neumann entropy is still positive. It's just given by this sum over I of pi log pi 1 over pi, and the pi's add up to 1 and they're positive. Okay, because it's a density matrix. What isn't necessarily positive is the conditional entropy. You'd maybe like to say that this means that your like expected surprisal, like log 1 over p is like somehow negative. That would more mean that like some probabilities p would be greater than 1. I agree that would also imply that some other ones would have to be negative to make them add up to 1. The answer is that it just doesn't make sense. You just can't think of this quantum conditional entropy as like coming from a sum over probabilities. All you can think of it as is just being defined by this difference between the global entropy and the entropy of a subsystem, right? And classically, there's always more unknown information about the entire thing than there is about some part of the thing, right? Because the entire thing is just described by describing each part separately. But quantum mechanically, that's not the case because you have entanglement. So you can have the entire thing be completely well-defined and well-known, but the state of the subsystem still be like noisy and imprecisely defined. Make sense?
Yeah, thank you.
Okay, and then finally, just like we had classically, we had this notion of relative entropy. We can define a quantum mechanical notion of relative entropy. And it's just, again, defined in the obvious way if you just take the classical definition and adapt it. So the relative entropy of rho relative to sigma is equal to the trace of rho log rho minus the trace of rho log sigma. Okay, so if rho and sigma commute, i.e. we sort of have a shared set of eigenvectors for them, then this just agrees with the classical definition. It just becomes trace rho log rho becomes sum over pi log 1 over pi, sorry, log pi log pi. And this trace of rho log sigma becomes like pi log qi. Okay. In general, of course, if I have two density matrices, rho and sigma, then rho and sigma won't commute, and there's not some shared set of eigenvalues, and the classical definition just wouldn't make sense. You couldn't apply it because you can't. You can't talk about the p of x and q of x because x is like an eigenvector and they don't have a shared set of eigenvectors. But even for this more general quantum definition where rho and sigma don't necessarily commute, you can show it's just a little bit more work than the classical case. The S of rho relative to sigma is always greater than or equal to 0 with equality if and only if the density matrices are equal. Okay. So this thing is really, it's a measure of how similar, how different rho and sigma are. Right, it's 0, it's positive if they're not equal to one another, it's 0 if they are equal. It's sort of more positive the more difference they are. So that's sort of like, it's really another measure of the distinguishability of rho and sigma, like the trace distance and the fidelity. But there's a big difference. This measure is sort of asymmetric in rho and sigma, right? So S of rho relative to sigma is not the same thing as S of sigma relative to rho. One is your expected extra surprisal. Roughly speaking, you expected extra surprisal if the real density matrix was rho and you thought the density matrix was sigma. The other is your extra expected surprisal if the real density matrix was sigma and you thought the density matrix was rho. So these are just different things. Okay. Okay. So using these properties of the relative entropy, you can prove all sorts of things you want to know about entropies. In particular, just like for the classical case, if we consider the relative entropy of the full density matrix, rho AB, relative to the reduced density matrix of A, tensor the reduced density matrix of B, then we get that this is equal to minus the entropy of rho AB minus the trace of rho AB log rho A tensor rho B. This log of rho A tensor rho B is just equal to minus the trace of rho B log rho A minus the trace rho AB log rho B minus S of rho AB. And of course, now you can just explicitly do the trace over B here and over A, B in the first term and over A in the second term. And then these just become S of rho A plus S of rho B minus S of rho B. Okay, so this relative entropy of the full density matrix minus the product relative to the product of the reduced density matrices is just the mutual information between A and B. Okay, and because this is greater than or equal to 0, and we find indeed that the quantum mutual information is greater than or equal to 0 as claimed. Okay, just like the classical one. Okay, so final thing I want to talk about is sort of a slightly more interesting inequality than just the mutual information being greater than or equal to 0, which is going to be something called strong subadditivity, which you'll hear about all the time if you ever do sort of quantum information. It's the most powerful and important inequality about quantum entropies. When you first see it, it won't sound very impressive or very interesting, but it really is. It's like super crucial to everything we know about quantum information theory. And the starting point for this is that it turns out that just like the trace distance. Actually, before I start talking about strong subadditivity, does anyone have any questions on the quantum mutual information, the quantum relative entropy, anything like that?
Just to quickly check, we define the entanglement entropy as the entropy of either the subsystem A or B, because they're the same when we split it.
Yep, exactly. Yep. So that's why it's really a measure. It's not the entanglement entropy of A or the entanglement entropy of B. It's the entanglement entropy between A and B, just because they're always the same. Okay, so just like the trace distance and the fidelity, the relative entropy is monotonic. Okay, so if I have some S of sort of rho AB relative to sigma AB, then that is always greater than or equal to just the relative entropy between rho A and sigma A. Okay, the sort of rho A and sigma A can never be more distinguishable. They can never be more different in the sense of having higher relative entropy than rho AB and sigma AD did. So classically, this would be, if everything was classical, this would be something pretty easy to prove. But in general, none of these things commute with one another. And the proof in the sort of full quantum setting is really highly non-trivial. And I'm not even going to try and give you sort of an intuition or prove a simpler version of it or anything. I'm just going to ask you to sort of accept on faith that this is true. We proved it for the trace distance. It's a homework exercise for you guys to prove it for fidelity. So it's like, this is just a claim that relative entropy is a good measure of distinguishability between the two. And it's true, so just believe it. Okay, so what does that mean? Well, it means that if I have some state, rho A, B, C, on 3 systems, then the relative entropy, rho A, B, C, relative to rho A tensor rho BC is greater than or equal to what we get if I just throw AC on both sides, right? So the relative entropy of rho AB relative to rho A tensor rho B. Okay, so using our definition before, the mutual information between A and B was relative entropy of rho B relative to rho A tensor rho B. Then this left-hand side just becomes mutual information between A and BC. And the right-hand side becomes the mutual information between A and B. Okay, can expand these out. So this is S of A plus S of BC minus S of ABC greater or equal to S of A plus S of B minus S of AB. Cancel out the S of A's from both sides, move some stuff across, and you get S of AB plus S of BC is greater than or equal to S of B plus S of ABC. Okay, so this is the conventional form of strong subadditivity. If you want to know why the name's called the name, subadditivity is just the statement that S of A B is less than or equal to S of A plus S of B, i.e. that the mutual information is bigger than 0. And if we take the special case where, let me get this right, we want to make B trivial. So B is just like a non-existent quantum system. We just delete B. Then this reduces to S of A plus S of C is greater than or equal to S of AC. Okay, so it's like a stronger statement than subadditivity, where you add in S of B's as well. And yeah, B's and all the things. Okay, so as I say, this sort of seemingly random inequality is at the heart of, I'll just say the heart of quantum information, because it really is. Like the information-y side of quantum information at any rate. There's a load of ways we can rewrite this that sort of make it more intuitive some ways. So we can rewrite it as S of AB minus S of B. Let's move the S of B across. That's S of A conditional B. Then we can add S of BC. Okay, so that's S of C conditioned on B plus S of B. And then finally, S of B minus S of ABC is minus S of AC conditioned on B. Okay, so this is just the ordinary sort of mutual information inequality, except everything is conditioned on this extra system B. Okay, so this is sometimes written as the mutual information between A and C, where all of it is conditioned on B, is greater than or equal to 0. Okay, so if we classically, this would be the statement that just even if we already know B, then there's a positive amount of like shared information of correlation between A and C. Okay, it's just an expectation of the mutual information between A and C, conditional on learning B over all the possible values of B. So you know this might not seem very surprising at all, but you've really got to remember. Go ahead. Someone have a question? Okay. That in quantum mechanics, these conditional entropies aren't even positive, right? So S of A conditional on B and S of C conditional on B can be negative. But somehow it works out that if they are, then S of AC conditional on B is like more negative, and that makes the full conditional mutual information. This is called sometimes CMI, conditional mutual information. Makes the full conditional information positive. But this should be a very surprising and non-obvious claim, and I haven't proved it. It just followed from this monotonicity of relative entropy that I didn't prove. So you know, you should. I'm asking you to accept something on faith that really shouldn't be obvious to you, but it is true, and it is a super useful result. If you really want to care, then you can look up the proofs. Yeah, none of them are terribly nice. There's one by Witten on notes on entanglement in field theory that I like quite a lot, but it involves a lot of background on infinite dimensional quantum mechanics and stuff, so it's not very good. But you can Google this. There's plenty of sources. I'm sure Nielsen and Chuang does it probably well. But yeah, this is some very non-trivial fact. Okay, so that is all I have to say. Any questions on the last stuff about strong subadditivity?
I have a quick question.
Yep.
It seemed like in the quick thing we did to come up with strong additivity, all we need is the fact that the relative entropy is for that one particular
is monotonic. Yeah, that's the proof that's hard.
I see.
Yeah, that's the the proof from that we did, and it's easy, it's trivial. But the proving monotonicity of relative entropy is like, it's just some work. I don't know. It's one of those things that is like incredibly important, but like proving it just involves like slugging away at some stuff, finding the right trick. But like learning the proof does not give you any more real insight about why it's true. It just leaves you feeling like, okay, this is some fact about matrices that happens to be true. Yeah, sometimes that's just the way maths is. Maybe we just don't know the like right, beautiful, intuitive proof that like makes it obvious why this has to be the case and why it's so nice. Yeah. Any other questions? Okay.
I think I'm
Yeah, you got a question?
Yes, maybe it's a silly question.
There are no silly questions, so I doubt it.
Why is so important this?
Yeah,
this
we'll
condition?
see. We'll see next lecture an example of it being important. It lets you, like, to some degree, it's important because it's like the one inequality you still have in quantum information, like beyond. I mean, for example, it gives all the other inequalities you have, right? Like mutual information being positive. That's a useful inequality, but it follows immediately from this by just taking B to be trivial. And so the conditions on B just disappear. So this is the sort of one most powerful inequality on entropies you really have. And so that's what you have to use. But we'll see next time we're going to do some very high level discussion of like quantum Shannon theory, of like, talking about like constraints on sending quantum information between different people and like what you can do and what you can't. And we'll see there strong subadditivity showing up as like, there is main way to like bound things, bound what you can do and what you can't. But yeah, I don't have sort of a intuition for you of like, yeah, it's just it's both complicated enough that it can encompass all the other inequalities you have, and it's like still true, and it's like simple enough to be useful. So you work with the tools you have, and the tool you have is strong subadditivity. That's the best I've got. I know it's not great.
Okay, thank you.
Cool. Any other questions?
Question, like the terminology like subadditivity, monotonic, and strong subadditivity. This reminds me of like probability theory and measure theory. They have those sorts
of what did you say first?
Probability theory and
yeah, I mean that's where the terms are coming from, right? Like yeah, like the classical information theory came first, and classical information theory is very closely related to probability theory. So yeah, what does subadditivity mean in measure theory? I don't know off the top of my head, but yeah, certainly, the if you do quantum information properly, like really properly, which no one does, and you care about like infinite dimensional stuff and all that sort of thing, then measure theory ends up playing a pretty important role. But like no one does that in practice, so we're all too lazy. Leave that to the operator algebra people.
Okay, thank you.
Any other questions? Okay.
I think.
Oh, yep.
I think I have another general question. What happens if I calculate the von Neumann entropy for a microscopically system or something? Do I recover the classical entropy?
Von Neumann entropy for what? For
large systems.
You mean by the classical entropy, you mean like the physics entropy, the like thermodynamic entropy?
Yes.
Yeah, so good. This is a good question. So the difference with thermodynamic entropy is that even if the system is actually in sort of compared to something like entanglement entropy, is even if the sort of whole system is in like a pure state, we'd say that has some thermodynamic entropy, right? Because there's a large number of different states that macroscopically look the same. If you took the density matrix of all states that look macroscopically the same, like mixed over all of them, or maybe like the thermal density matrix of some system or whatever, and you took that as your thing, that will give you the like usual entropy you're used to in physics. Yeah, so the von Neumann entropy of a particular state, namely a mixture over all microstates. Is that clear?
Okay. Yes, thank you.
Cool. Okay. Cool. Thanks, guys. See you on Thursday.